There we go. So I'm Jean Benoit. I'm a professor at the University of New Hampshire. And so today I'll talk about how we can use monitoring while drilling to do ground characterization and how that can save you some money. So the first thing I'd like to do is to acknowledge some people that I've worked with, some students I've worked with and colleagues. The presentation today involves the work of Stan Zakowski and Kevin Stenson and Evan Longstein. Stan and Kevin work for Sanborn Head and Associate now, but they were former grad student and were involved with the MWD. I've had other students from foreign exchange students, and I have a research colleague also in France with whom I've been working on MWD. So the outline, I'll introduce what MWD is, because probably some of you don't know what this system entails. We'll look at how we analyze or recorded drilling parameters, and then I have a deep foundation case study that will highlight how using MWD can really save you some money, which is the objective of this webinar, and I'll conclude. So let me start. We know there's a panoply of field methods out there, in-situ testing method. This is a figure from Professor Main at Georgia Tech showing all kinds of different tools. But what you don't see in there is drilling of boreholes. Drilling of boreholes really should be considered an in-situ test method, and it's nowhere in there. DFI increased testing saves money, so MWD will save money without increased testing actually, because most of the things you do involve drilling boreholes. And if you can get that information from the drilling process, then you're getting some testing at no additional cost. So major uses of geotechnical boring, and you know, I know most of you know this, but we want to define the geologic stratigraphy and the structure of the subsurface there, whether it's in soils or it's in rock. We want to get some samples for geotechnical testing. We want to perform some in-situ tests. So for instance, SPT, right? We drill a borehole, we get to the depth that we want to do the SPT, and then we do it there. Installing of instrumentation, whether it's inclinometers or monitoring wells, foundation installation, tiebacks, micropile, drill shafts. We can evaluate existing structures. For instance, a dam, we want to look at the integrity of the dam. We're going to be drilling some boreholes in there, maybe do some grouting later on. Assess performance following ground improvement to see if the method that we use, let's say deep dynamic compaction, has worked. So we'll do tests before and after. And of course, environmental assessment and remediation. So there's all kinds of uses for geotechnical borings, and there's thousands and thousands of boreholes that are being drilled annually in the US and around the world, obviously. So let's talk about MWD, so measurements while drilling. Essentially, it's a computerized drilling monitoring system, and that continuously and automatically record all aspects of drilling at any depth interval that you wish to select. So typically it'll be between 1/2 inch and 3/4 of an inch interval. And it's a real-time display, so you can see here there's a computer monitor, and the information that you see here is what the driller sees. Okay, the data is stored in real time, and the data displayed in real time, sorry, and the data is stored electronically. This is not a new system or new process. It was introduced in the oil industry, and it's been part of geotechnical practice since the 60s, mostly in Europe and Japan. I was first introduced to it back in '92 when I was on sabbatical in France and Italy. And in Italy, we were doing some drilling, and they had a system then. It was, a very bulky system, but I was very impressed with the fact that it was recording all the drilling aspects. And I came back here and tried to get funding from National Science Foundation, but a lot of the reviews were coming back saying, well, this is way too practical for us. So it's taken a while for the thing to get going because of the resistance a little bit from academics, which I'm part of academia. But it's for stratigraphic studies, detection of cavities, and grouting program. So what you have in the system, essentially, you see the outline of the drill rig in there. You have an interface recorder, and it goes to a junction box. So this is the recorder. This is what the driller will be looking at. This is the junction box in here. And you have a number of sensors that you install on the drill rig. These sensors, you don't have to have all of those, but the sensors that can be installed on a conventional drill rig is a sensor to measure the depth, the down thrust, the hole back pressure. That would be in cases where the drill string is very heavy. You actually have to hold it back because of that added pressure. That's usually not typical in drilling, at least in this country. Torque, rotation rate, vibration. You can also measure drilling fluid injection pressure as well as drilling flow going in, and you can also measure it going out. The junction box, so all these sensors are connected to the junction box, and which is powered by the rig battery. So 12 to 36 volt is what you need in there. And then you have the drilling parameter recorder. In the past, we used to call MWD DPR because of the drilling parameter recorder, but I think the right nomenclature is MWD. It's easy installation, and the operation of the system really does not interfere with the drilling process. So here's some slides showing the installation of the system. This recorder here is very bulky. That's the first recorder that we purchased back in the late 90s, and now we just purchased a new recorder, which looks more like a tablet. And then you have the various sensors here. These are pressure sensors. So for instance, if you want to measure the down thrust, you're measuring the hydraulic pressure, right, in the cylinders. So basically what you do, you go in the hydraulic line there and you put a T connection, and then you put a quick connect there so you can connect your sensor. So you have a sensor for, if this is a hydraulic rig, then you'll have a sensor for the torque, that will be hydraulic. You'll have a sensor for the down pressure. You'll have a sensor for the water pressure. And everything is connected to the junction box in here, and the junction box is connected to the recorder. Here we have we call the driller's button, and this is a close-up of it. It's just it's set up with a magnetic base, so the driller can put it anywhere. And basically, it's meant to be hit whenever the driller adds a rod, so the system knows that you've added a rod. And it's a very big button because we know drilling is very dirty, and drillers have big hands and big gloves, so they don't need a little fine thing to push. So this works very well and very convenient for them. The depth sensor is just basically installed on top of the tower in here. So you have the sensor, and you have a potentiometer in it, and there's a string that goes into the top in here to the head. So as the head goes down, the drill goes in the ground, it pulls on that belt. It's sort of a belt in there, and that gives you the depth. And it only records past the maximum previous depth. So it doesn't keep recording when you go up and down with the rod. It just measures all of the new penetration. And that's why when you're done with penetration of one rod, then the driller will hit that driller's button and say, okay, now we've added one more rod, so we can keep adding to the depth at that point. Here is a view of the flow meters. So here we have the inflow. So you have the water pump in the background here. We have the water pressure sensor in here. And so we measure the pressure and the flow. And then what we did on this project I'll be presenting today is we also measured the outflow. So this is not commonly done, but I really wanted to see what was coming out of the ground. So if you have fractures in the subsurface, then you're going to be losing some of your inflow. So by measuring the outflow, putting a T connection in here and running it through the flow meter, we can see how much we're losing. This is the rotation sensor. It's a electromagnetic sensor, and on most of the rigs, especially the hydraulic rigs, you have the drill head in here, and it has a series of bolts, usually 10 to 12 bolts. And so what we do is we set up this sensor maybe about a quarter of an inch or so from the bolt. And what it does is it measures, it knows whenever a bolt goes by, it counts. And so you can put it in the computer system that say you have 12 bolts in there. Every time you see 12 bolts, that's one rotation. That way it can measure the rotation rate. So this is action pictures, I guess. So this is a project in Boston in here. This is another project in Boston, and this is out in Colorado, working with the U.S. Bureau of Reclamation. They had the same system, and I went out there and helped them out set the system. And one thing that you can see here is in all these cases, what is the driller doing? The driller is actually looking at this system. And this was a little bit, it's an old system, so it was thermal printing, so the driller would actually see a little squiggly line on a piece of paper, but you could also see the digital display, so you could look at the numbers and see what was going on. With the new system, you have really nice graphic. So the driller is really involved in this, and it's kind of cool for drillers the first time they see that, because, for instance, you'll ask them, you know, what's the RPM? What's your rotation rate? Usually they have no clue. They've never really asked themselves that question. They're very surprised to see what number they're showing there when they're drilling in different material. This is a typical output using the software from the company that we use, Jean-Luc, they're in the south of France. So I translated here, it's in French in this case in here, but their software can do various languages. But you have the advance rate in here that you record the thrust, the mud pressure, the torque, the RPM, the rotation rate, and the whole back pressure. In this case, they had whole back pressure. So you can see, just looking at this quickly, that there are some differences as you go through various material. And now I will highlight that with a couple profiles later on. So let's talk first about drilling parameters. There's different categories. There's the parameters that are imposed by the drilling method, but those are not necessarily digitally recorded. So the tool type and diameter, the limits of the machine, the injection system, and fluid type. So that's imposed by the drilling method. It's important to note those, but it's not recorded. You have to put that down on your data sheet. And then you have the machine parameters that are controlled by the operator. So the driller is really controlling the thrust on the drilling tool. He's controlling the rotation rate. He's controlling the drilling fluid flow rate. I'm saying he here, but it could be she. Okay, and that you'll see later in the presentation. The machine parameters are really from the ground response. So the driller is imposing some parameters, and then the ground is responding to that. So the advance rate, the torque, the fluid injection pressure, the drilling fluid flow rate, and the whole back pressure is really that response. And then you have all the non-control parameters, the tool wear, the changes in drilling fluid composition, those are non-control. So this is what you would record. I'm just putting here, and this is in meters. I have another example in feet, in English units. So you have your penetration rate in meters per hour in here. You have your thrust in kPa, the torque in kilonewton meters. So you're plotting all of this information in there. So you can either use the system from the company, or you can just download the data on the spreadsheet and manipulate the data however you want. So what we have to do when you get that data, you're getting a lot of information. So you have to concatenate the data. So that means you have to put your data in order. So, you know, every little section that you drill, you just put them back to back, and then you remove the drilling artifacts. So when you change rods, you're going to have some really numbers that are meaningless. So you're going to remove that, clean that up, convert into appropriate engineering units, and remember, drillers in this country don't like meters and kPa. In fact, my students love meters and kPa, but they have no idea what it means. And then you're going to filter the signal noise. So what we've done in here is we use a sliding average. So in this case, we use the 20 centimeter, which is you take data from 20 centimeter before and 20 centimeter after, and you do that average. And that gives you enough of a signal to detect changes. Then what you can do is you can combine these individual drilling parameters into expressions of energy or empirical indices, which will reflect the resistance of the geologic material to drilling. So it's in essence, you're normalizing the effect. So by combining them, you remove the effect that from the driller and the drill rig and the drilling tool. So that way you can compare from one side to another. And it'll allow you also to develop specific or material specific expressions for your site. The various methods that can be used, you have compound parameters here, the Somerton index and specific drilling energy, etc. They're not very complicated. You're just taking the parameters and you're combining them. And so that can be helpful in looking at the data. And again, it normalizes the information. So it's a lot of practical benefit. You can correlate SPT with specific drilling energy. We've done in here, showing that the SPT and the drilling energy really correlates very well. You can fill gaps in stratigraphic details. You can reduce the number of SPT boreholes, and in rock you could do destructive drilling, so using a roller bit rather than coring, and you can create site-specific correlation, and certainly you can do more holes for less money. As we know, doing SPT boreholes is very time-consuming. This is a way where we just did water pressure over troughs, and it gave us a relationship where we can see where we had little seams in here in the stratigraphy. So here's a case study. I think I have less than 10 minutes now. So this was used for a 21-story building in Boston. And the project was, we needed to evaluate the rock quality. The design requirement were fairly heavy column loads with a spacing of 4.5 to 13 meters, and we needed to do a 2.4 to 3 meter diameter drill shaft, a drill caisson socketed in rock. So what we did is drill 8 15 millimeter diameter boring at the caisson locations, and to a depth of 47 to 54 meter, using rotary advance and water drilling fluid. So the core lengths that were done in NX size is 14 meter to 21 meter of core. The rock in Boston, a lot of it is Cambridge argillite, and there's some zones of diabase, sandstone, and basalt. But the argillite is a soft to medium rock, slightly to severely weathered, sound to extremely fractured. So you go really a big range in there. It's aphanitic, which means you can't see the grain with the naked eye. Very shallow to steeply dipping bedding planes, so very close parting along the bedding planes, and the RQD is really can be from 0 to 80, 90%, okay, when an average of 40 to 50. So when you drill through this material, it's very easy for the driller to induce fractures because of the type of material you're dealing with. And of course, you know, you have the driller here always using a fine-tuning tool getting the core out. Well, that doesn't help either. Here's a slide showing various sections of core boxes. So you can see you can get all kinds of stuff in there. Well, what do you do with this when you're trying to do your design? Are you looking at a joint, or are you looking at a break that was induced by the driller? So what is the real RQD in there? So that's what we did in there. We looked at the data, and say this example here, just looking at the drilling parameters from 45.7 to 48.7, we could detect where some of the fracture zones are. We can detect this section here where we have really sound database. And the outflow, if we're not getting anything out, that means there's a lot of fractures in there, right? Then you can look at the compound parameter. You can we looked at all the methods basically, and you can see when you have something very sound, some of these parameters will be very, very smooth. So you're gaining some experience as you do this. You start comparing the readings that you get with what you recover from the ground, and then you can build your database that way and your expertise that way. This is looking at a full borehole here going from 34 meters to 51 meters. So you have diabase, basalt, argillite, sandstone, argillite, basalt. So a lot of material in there, and look at the RQD. So this is based on what got out of the ground. So you can, looking at this data, I know looking at a presentation is a little hard to be able to analyze these things, but you can look at some zones in here. You have a fracture zone where you have a really significant drop in mud pressure. So that's a fracture zone in there. You have a decrease in here, a change going from basalt to argillite in here. So you're looking at the changes. In here you got very high RQD, and you can see that the penetration rate is fairly constant in there. And in here you have a severely fractured zone, so you have a very high penetration rate. This is just looking at a shorter section. This is an English unit, and what I did is I took pictures of the core boxes and try to lay them out in there. But you have a 5-foot core run in here, and you only recover 60%, and the RQD is 0%. So what do you do with this? Where is what in the ground? Okay, so you can look at these things and say, wait a minute, I got a high penetration rate. There's a fracture in there. There's some fractures in there, okay, at these locations in there. And then you can start seeing differences in the material as well, going from diabase to basalt. So this is with just the parameters, and then this is with the compound parameters. So again, it looks like a bunch of squiggly lines, but once you sit down and start comparing the data, you can really see the changes. And some methods will work better than others depending on the type of material you're drilling through. This is from the same site. This is the overburden. So it can get very complicated. And again, if you don't have to do SPT everywhere, you can really use the MWD and do more boreholes and refine this stratigraphy. So in this case in here, the MWD showed that the in-situ rock quality was much better than shown by the logging from the engineer and the RQD of the cores. So the cores were really damaged during drilling and during core extraction. So by using the MWD, they were able to reduce the caisson length by 50%. And so back in 2007, that resulted in a decrease in cost of about $500,000. What we did after this project, I recovered all the cores, and I had a master's student do a whole bunch of testing, 152 lab tests, did some unconfined compression, did some Brazilian splitting tensile tests, and some point load tests, and try to compare these values of strength with some of the drilling parameters. And This is a, bit of a shotgun graph, but this is the unconfined compression and this is the tensile strength versus the Somerton index and the drilling energy. And we can see there's a little bit of a trend with the drilling energy and the tensile strength being more of a fundamental property. It's not so much affected by the type of test. Of course, if I did this in a log scale, it probably looked better, but I just try to do it so you could actually see the data in there. Point load is very interesting. If you look at the argillite in here, what we came up with for the point load, typically you look in the literature, this is what it's going to give you. It's going to say that the unconfined is equal to 24 times that point load strength index. But from the data that we did, it's really more like 13.3. That's quite a bit of a difference. If you're going to use this, you're going to be, it's not on the conservative side, definitely. So a little bit more in here. I think I'm running out of my time allotment. So in conclusion, MWD is really an in-situ test and can easily detect all the stratigraphic changes in soils and in rock. You can pick up thin layers, seams, lenses, gouge. You can differentiate between fractures that are natural or drilling or driller induced, and you can get a better idea of rock quality. You can use it in any material. There's no limit of applicability, unlike most in-situ tests. And it's easy to implement, and the drillers love it. Of course, at some point, we need to standardize this system. And this is my last slide. I want to thank you and show the evolution there from the driller to this is, I picked that up on, this is in Sweden. So you can see a lady doing the drilling in here. Their machines are really automated, so it makes it more convenient, but she's looking at an MWD system. And so I think hopefully we'll get to that point in this country also. And this is one way also to encourage younger people to get into drilling. There's a computer, you can get the data and really do more than just putting a hole in the ground. So thank you.